We are done with the MOS capacitor. Let's take a look at Mosfet. Now, Mosfet has many acronyms, including IGFET, which stands for Insulating Gate Field Effect Transistor, MISFET, which stands for Metal Insulator Semiconductor Field Effect Transistor, and MOS, which stands for Metal Oxide Semiconductor Transistor. Now, this figure shows you the perspective view of an N-channel MOSFET. It is a 4-terminal device consisting of a P-type substrate in which two N plus regions, the source and the drain are formed. Now, the metal plate on the oxide is called the gate. Heavily doped polysilicon, or a combination of a silicide such as tungsten silicide and polysilicon, can be used as the gate electrode. Now, the fourth terminal, which is not shown in this figure, is an ohmic contact to the substrate. Now, if you want to know the device parameters, these are the channel length, which is denoted by capital letter L, which is the distance between the two metallurgical N plus P junctions. The channel width, which is denoted by letter Z. The oxide thickness, denoted by small letter D. The junction depth, which is denoted by R sub J. And the substrate doping, which in this case is not indicated, but it's denoted by N sub A. Note that the central section of the device corresponds to the MOS capacitor. That's why we discussed MOS capacitor prior to MOSFET. Now, if you take a look at the history, the first MOSFET was fabricated in 1960 using a thermally oxidized silicon substrate. The device had a channel length of around 20 micrometers and a gate oxide thickness of around 100 nanometers. Although present-day MOSFET have been scaled down considerably, the silicon and thermally grown silicon dioxide used in the first MOSFET remains the most important combination. And most of the results in this discussion are obtained from the silicon dioxide system. Now, what are the basic characteristics of MOSFET? The source contact is used as the voltage reference throughout the section. So when no voltage is applied to the gate, the source to drain electrode corresponds to two PN junctions connected back to back. So the only current that can flow from the source to drain is the reverse leakage current. Now, when we apply a sufficiently large positive bias to the gate, the MOS structure is inverted so that a surface inversion is formed between the two N plus regions. So the source and drain are then connected by a conducting surface N channel through which a large current can flow. And the conductance of this channel can be modulated by varying the gate voltage. In addition, the substrate contact can be at the reference voltage or is reverse biased with respect to the source. So the substrate bias voltage will also affect the channel conductance. Now, for this figure, we present a qualitative discussion of MOSFET operation. So let's consider that a voltage is applied to the gate, causing an inversion at the semiconductor surface. So if a small drain voltage is applied, electrons will flow from the source to the drain through the conducting channel. Thus, the channel acts as a resistor and the drain current is proportional to the drain voltage. Now, this condition is a condition for a linear region. This is indicated by the constant resistance line in the right-hand diagram. Now, when the drain voltage increases, eventually it reaches a saturation point that is denoted by V sub dsat, at which the thickness of the inversion layer xj near y is equal to L, is reduced to 0. So this is called the pinch off point, as you can see in figure B. Now, beyond the pinch off point, the drain current remains essentially the same, because for V sub D greater than V sub dsat at point P, the voltage V sub dsat remains the same. Thus, the number of carriers arriving at point P from the source, or the current flowing from the drain to the source, remains the same. And if this happens, you reach the saturation region, since I sub D is a constant regardless of an increase in the drain voltage. So the major change is the decrease of L to the value L prime. Okay? A decrease in the value of L, as you can see in figure C. So from L, it becomes L prime. Now, carrier injection from P into the drain depletion region is similar to that of carrier injection from an emitter-based junction to the base collector depletion of the bipolar transistor. So if you are paying attention with my discussion, or to my discussion of a bipolar transistor, you will understand what I am saying. Now, we now derive the basic Mosfet characteristic under the following ideal conditions. Letter A, these are the ideal conditions. The gate structure corresponds to an ideal MOS capacitor. That is, there are no interface traps, fixed oxide charges, or work function differences. Letter B, only drift current is considered. Letter C, you have carrier mobility in the inversion layer is constant. Letter D, doping in the channel is uniform. Letter E, reverse leakage current is negligibly small. Letter F, the transverse field created by the gate voltage in the channel is much larger than the longitudinal field created by the drain voltage. Now, the last condition that I have mentioned is called the gradual channel approximation, and generally is valid for long channel MOSFETs. So under this approximation, the charges contained in the surface depletion region of the substrate are induced solely from the field created by the gate voltage.